I'm Fabian. I work at CoreOS, and I'm also a Prometheus maintainer. I've also been a Prometheus maintainer before at SoundCloud, so I've been doing this stuff for quite a while now. And I want to talk about alerting in cloud-native environments. The original title was alerting based on Timeseries, but this sounds a bit more fun, I guess. But we actually want to talk about alerting with Timeseries. And just to start out, very theoretical and boring, what's a time series? A time series is a stream of values, and they are tuples of timestamp and an actual value. And the timestamp is always monotonically increasing. And to give meaning to the stream of samples, we have some sort of identifier. And that's, in our case here for Prometheus, a metric name, HTTP request total here, which we then split out into more granularity using labels. So don't have just one counter, we have several counters for every instance we have, for every path we have, for every status we have, for each unique combination of labels. And then we have several time series associated with a single metric. And if we have that, we can do interesting stuff, right? We have now data that we can query. In this case here, we query all time series for this particular metric and this particular job label. And because they are counters, we now want to get the per second value. So from just a counter counting up requests one by one, we now want to know what's actual over the window of the last 5 minutes, my requests per second that my applications are experiencing. And applying this to thousands of time series gives you a pretty big result, which doesn't really give you any good insight in what you're looking at. That's why you have aggregations. You can aggregate along these label dimensions. So here we want to preserve the path and status dimension, and what we get back is unique tuples of path and status labels and the currently associated recurse rate. And that's actually what Prometheus is doing. So Prometheus is a monitoring system and time series database, and it knows how to talk to your service discovery system like Kubernetes, and discovers all things that are interesting to monitor in your infrastructure. And based on this information, it goes out and collects sample data from these so-called targets, which can be routers, switches, nodes, your microservices, basically anything you want. And having stored that in our database now on our Prometheus node, we can also query it in sort of the query language we have seen before, and thereby expose it via our HTTP API to things like Grafana, our own UI, etc., etc. But it's mostly geared towards basically graphing stuff, either for dashboards or on demand if you want to do investigations during an outage. And now we want to do alerting. And how we do this? Well, we have a ton of data. We have millions of different time series and billions of data points associated with them. And of course, it's quite an appealing idea to just do all the fancy things. We know from the terms like machine learning, anomaly detection, correlating stuff, making everything self-healing, because we have big data, right? And big data generally means we can make everything magical. So for Prometheus, we decided against this very strongly. And the simple reason is that we're actually monitoring at scale. We really urge our users to instrument applications way more than they do by usual means now, which means there's way more data than in the past. And while machine learning, etc., might work quite well at a smaller scale, if you have little data, if you scale it up by a factor of 10, 100, 1000, something will always correlate, right? If you just look enough, some curves will always sort of add up and seem to make sense without having any sort of causal relation. And in the end, to eliminate these false positives, which will be very bad for alerting, right? Because we'll get paged for nothing, you will have to put in huge efforts. The problem is if you eliminate very aggressively, there's a good chance that you will somehow also cut out some alerts that should actually be firing because now you have a false negative. And if you're alerting, false negatives are not really an option. So if your data center is burning down and you don't get paged because your machine learning thought everything is probably okay, doesn't really work. So the question is, having all this data, can we still come up with a comprehensive approach that's easy to use and gives you full coverage and insight to alert on things going wrong in your infrastructure? And if you think about it, our time series represents quite well the current state of everything, of our nodes, of our microservices, of our routers, everything that's basically instrumented. And for everything that's running, we have an idea of how it should be running. That's commonly known as an SLA or SLO. And if you don't have one, you should probably think about what it should be. But we generally can define, based on a current state, whether the current state matches this desired state. And if it does not, the delta of those two, that's what you want to alert on. It's actually pretty simple. So what does this mean practically? Practically, this means everything that's an alert, and we consider alerts usually things that page me at night, right, or during the day. Everything that's paging should be urgent and actionable, right? It should be a direct problem for our users. If the user is not impacted, there's not necessarily a problem. And the user can be anything here, right? If you are writing a microservice, which is sort of serving data for other microservices, these are your users. If you're facing customers directly, these are your users, etc., etc. And you only really care about the boundary between your system and your user. And that is also exactly where your SLA is defined. And there are 4 golden signals, which are sort of meant to capture things to alert on. And one of them is latency. If a user makes a request to whatever service you provide, they expect a timely response. That might be a few milliseconds, a few seconds, maybe even hours, but there is certainly some sort of time frame in which they expect a response. So that's a good thing to alert on, obviously. Then there's traffic. If your application should receive approximately 1,000 requests per second and is receiving 0, something's probably up. It might be on the way between your user and your system, but it might also be that your system is just sort of not even accepting requests to the point where it can measure them. So that's also something to watch out for. And closely related, we have errors. If your users make requests and get not served the response expected because of errors on the server side, you're violating SLA most certainly and should definitely alert on that. And the 4th golden signal actually is not symptom-based, which is kind of breaking our paradigm here. Instead, it's cause-based. There's a reason for that. But first of all, what is cause-based alerting? Causes are everything that potentially lead to problems, lead to symptoms of problems. So if I can't connect to a database, which is sort of my downstream dependency, this might cause me not being able to serve a request to my user, but it does not necessarily imply it, right? If I'm caching for long enough for my dependency to recover, it is just a potential cause, but not an imminent problem. And in general, these things should not be something to notify someone about in a disruptive manner. These are usually meant to provide helpful context. If I get paged for a high error rate of my service, I can now look at what currently cause-based warnings we see. And the only exception is sort of our 4th golden signal, which is saturation/capacity. That can be stuff like file system running full, memory running full, basically a lot of stuff running full. And the reason why we make this sort of more of a cause-based thing is that if we run out of file system space, out of memory, etc., the effects of that are usually quite critical and don't resolve themselves quite easily. A file system running full might take hours of migration work or might even corrupt your data. So these are things that you really want to catch early because if they happen, they are not maybe a cause of something, they are most certainly causing severe symptoms in the end. So, so far for the theory, and that applies to everything that is not bound to Prometheus in any way. But we can look at how Prometheus sort of implements this idea of alerting. And we have our small DSL where we can define an alert name and we can associate it with a condition. And the convenient thing here is that these conditions are expressed as Prometheus query language strings. These are the same queries that you use for dashboarding and investigation during an outage. So everything you can graph, you can alert on. And that's extremely good because, first of all, we hopefully know the query language already. And also, if you get an alert, we can directly click on the condition that triggered it, and we'll see a graph that relates to exactly this. And then there's some other stuff in there, like the for duration, which is sort of a grace window before we actually send out an alert, which is supposed to prevent flapping alerts, right? If a problem resolves itself within a reasonable amount of time, there's not really a reason to sort of propagate this alert to any human. And there are labels and annotations, and we will see later how these are used. And if you have seen PromQL before, it's, or in the example before, we don't get just back a single result, right? We get back sort of a vector of label pairs associated with a value. And that's exactly what we get in our condition here. And every element in our result is one single alert. So as an example, we are monitoring etcd, and etcd exposes a metric about itself, which is called etcd has leader. And it's 0 if etcd does not, if this node does not see a leader in the etcd quorum, and 1 if it does. And obviously, not seeing a leader is pretty bad, and 1 is okay. And here A and B obviously are in trouble. And an alert detecting exactly this condition would be as simple as saying alert etcd no leader, and then the condition being etcd has leader equals 0, which filters every time series that does have the value 0. Filters out every time series having the value unequal 0. Which means that our result basically is exactly the two instances we have seen before, which don't see a leader at this point in time. And each of these now form one alert, and what we do before sending out the alert is we attach a label of alert name, and we attach the severity label, which is part of our alerting definition. And this label will be used later on to make a routing decision on how and who should be notified. Who should be notified and how. So these are just arbitrary labels we can attach to any alerts being sent out. To make it a bit more complex and see how we can actually design a bit more complex real-world kind of alert, we have some time series here. Or we have two metrics, one counting requests and one counting the subset of errors of these requests. And these are split out by certain labels, like the instance, so every sort of process of our microservice, by the request path being used, and by the request method. And we want to alert on error rate, the errors being too high. And we can start as simple as saying alert high error rate, and then let's take just all these time series we have for the error rate, for the errors we counted, and take the per second value, because that's what we're interested in. So we take the per second value over a 5-minute window. But this will still give us, for every single instance, pass and method combination, one potential alert. And that's, of course, too noisy, right? We don't want to get 20,000 alerts if sort of the whole service is buggy. And to mitigate that, we use an aggregation. So we apply a sum, which condenses this whole thing nicely in a single value. And we can see here that apparently our service is experiencing 534 errors per second. Yeah, okay, that's bad. And because we don't want this to happen, we set a threshold and make this alert trigger if the value is greater than 500. And so the result we get is sort of what we expected. We are alerted if this condition hits. The problem here is this absolute threshold, because it's quite fuzzy. What does this actually mean? Like, is this a 5-node service, a 5,000 node service? How many requests is it getting? Right? And whenever it's totally dependent on the total traffic we are receiving. So over the day, we might have a sort of curve which changes as users in sort of busy regions log onto the system or something. We might just get more traffic over months or weeks of time. Or we might just have a traffic spike because you were mentioned in the news. So there are many, many different ways that can sort of change the number of requests we are getting, and the error rate we are seeing depends directly on these requests. And the semantic meaning of this alert changes basically based on values that are not represented in the condition. So what we ideally want is we want this sort of threshold to be adaptive to the total traffic. And we can do that easily enough by just dividing the error rate, which we calculated, by the total number of requests, right? And now we have a fraction, which is certainly way closer to what we want. So if more than 1% of our requests are errors, then we want to trigger an alert. And now the picture looks like this, and that's certainly way closer to what we want. And it's not right anyway, because we are losing a lot of detail, right? And we have this label-based query language, or all these time series having a lot of granularity, and what we're condensing them into a single value. And this unfortunately can cause signal cancellation. So let's say you have one recast pass which is hit very, very rarely, like a contact form, right? It's maybe hit like once an hour compared to your index page, which is maybe hit like 200 times a second. And even if your contact form errors every single time a user wants to see it, it will not show up in this result because it's totally overshadowed by the high traffic your index page receives. And the threshold is somewhere down there. So we are certainly having a problem that it's not detected at all. Luckily, we can also solve this. As we've seen before, we can preserve certain dimensions in our aggregations, right? So we have all these time series, and we say, yes, aggregate, but keep certain things around so I can have more detail. And if we want to preserve the instance and the path label, we achieve exactly that. So what we get back here is a nice per instance path combination of the total error rate. And in this case, the previous example will be reliably sort of detected. And it's still wrong, intentionally, of course, just show you what can be wrong, because we're preserving the instance label. And in the case of a microservice, for example, that's actually the dimension along which we tolerate failure, right? Because we are building a resilient system that can handle certain errors. And in a horizontally scalable system, a single instance misbehaving is certainly one of them. So with the alert as it is, if 1 out of 1,000 instances misbehaves, we will get paged. And there's nothing really we can do. We can probably shut down the instance and bring up a new one, but it's not necessary because there was no problem for our users to begin with. And we're just sort of going to burn out because we get all these nonsensical errors. Alerts. So the reason, the answer, of course, is just pick different dimensions. And Prometheus comes with a really nice query language feature, which is sort of the inversion of sum by, which is sum without. So we specify the dimensions we want to get rid of, which is way safer, right? Because we are not necessarily aware of all the dimensions that our metric has, but we're usually aware of the dimensions we are fault tolerant along. And in this case here, it's the instance. And we say, okay, aggregate everything away but the instance. And what we get back is, we sort of get back the most insight we can, because it will preserve the path as well as the method, which was not considered before. And this is sort of the alert we would like to end up with. And it's a 3-line alert, which will cover 5,000, 10,000 microservice instances. It doesn't matter, because it's acting based on a pool of time series data. And you don't have to sort of tweak anything if your infrastructure roughly stays the same, or the deployed things in infrastructure stays the same. It will just scale automatically sort of with your infrastructure. You don't have to install any new checks for every new thing you deploy. It's sort of adaptive. Yeah, and that's actually a typical alert for symptom-based pages. And ones for latency look pretty similar, and you will also observe that if you're sort of having a typical microservice architecture, that almost all alerts will look like this. And that's actually a good thing, because it makes things simple, right? There's no black magic involved here. You have a few distinct patterns to stick to get reliable alerting covering you end to end. And don't have to consider any of these potential tens of thousands of causes leading up to the problem. And now to an interesting part, the capacity saturation alerts. They are kind of a different class, but they're also following a very similar pattern every time. So a typical thing to detect is my disk is running full. And what we typically do nowadays is we probe every sort of node or file system and check, okay, how full is it? And if it's at 70%, everything's good. And if it's at 80%, everything is good. And if it's at 81%, then we will page someone, because obviously everything changed between 80 and 81. And this has several problems. First of all, you're not using 20% of your disk, just to have this like 20% buffer to react if your disk does run full. But it also is triggered immediately if you just add a 2 kilobyte file, putting it over the threshold, even though afterwards nothing changes ever. And it also doesn't detect if your disk is almost free, but then sort of extremely quickly filled up by some sort of spammy software. It will only alert you if it's almost too late. So the solution here is what we do in Prometheus. We have history, we have time series. We don't just know what's happening now. We don't just know that the current fullness of our disk is 80%. We also know what it was 10 minutes, 30 minutes, and 1 hour ago. And based on that, we can actually look at the development of the data over the last hour in this case here. And look at the metric telling us how many free bytes there are on any particular file system. And based on this 1 hour window from now to the past, we can do a linear regression and just predict into the future where things will end up if it continues as it does. And we do so for 4 hours in our case here. And if this prediction tells us that in 4 hours we will have 0 or less free bytes on our disk, then the current development on this disk is indicating that we have to do something. And this holds true no matter whether we are at 80%, 90%, or 10% of this usage, right? If you're at 95% and you're at a 1 megabyte file but don't nothing else afterwards, this alert will not trigger and wake you up because there is nothing to be done. And this sort of applies universally for all sorts of saturation capacity alerts, right? If you want to alert on file descriptors running out, inodes running out, memory running out, this sort of always applies. And now we're looking at annotations. Annotations are this other thing that we have seen before, and they allow us to just tag additional non-identifying information to alerts. So if you want to sort of provide a more insightful human-readable message with our alert, we can just add some text in here. And we can, as a really nice property, we can use the labels of our result. So if our result has labels for the device in question, the mount point, and the node it's running on, we can all add this into our message. And this is also, again, a full alert which will cover every single file system on every single hard drive, on every single node of your entire infrastructure. So that's sort of, okay, that's how we write alerts, how we define what is problematic and what should be alerted on in the first place. And now we come to Alert Manager, which is sort of a distinct component in the Prometheus ecosystem. And no matter what system you have, you should have some alert management layer. And how it works is that Prometheus evaluates the rules which are specified. It collects the data, stores it, and immediately evaluates the data in alerts, which is really nice because everything is self-contained, right, and not crossing failure domains. And if it considers some alert firing, it will push it out to Alert Manager. And the Alert Manager is then responsible to do the sort of more fine-grained stuff like determining which on-call person should receive which alert, which has no real purpose being directly in your monitoring system. And it has some more important functions, actually. So if we consider these rules we have defined to just be rules somewhere, we don't really care about which Prometheus server they're coming from. But they are these things that are just emitting streams of alerts going your way. And you probably see below here, that's probably a pattern that you have encountered when being on call, right? You get woken up at 4 a.m. And you get a page telling you the latency is high for service X in zone EU West for this request pass and this request method. And you say, okay, and then you get the next page telling you the same thing, just with like some slight modification. And this just continues for 10 minutes. You're getting pages and pages and pages and pages, and they're all sort of tying back to one single incident. So the question is, why are you getting 20 pages if there's one problem? And we actually want it to be this way, after all, because we want this insight and granularity, right? Because we don't want to overshadow problems by being too generic in our alerting rules, as you have seen before. And how we can still solve this is with an alert management layer. And what the alert manager does is it gets a stream of alerts and looks at it, evaluates how it should be actually digested and brought to the user by grouping it together along certain label dimensions, based on these labels making routing decisions, so which team should be paged about which service, and also deduplicating in case you have several Prometheus servers that are sort of emitting the same alerts in HA deployment. And what we then get is we get one single page telling you you have 15 alerts for service X in zone EU West, and these are the rough problems here: high latency, high error rate, and cache server being slow. And that should be almost everything you need to sort of know what is up, and then getting to your laptop and actually start investigating and handling the incident. And all the individual alerts you see here, it's actually not too important. Just the big picture is what we're really interested in. And there are also some other stuff. So we have, on the one hand, silencing, right? So if you take a service into maintenance, you can silence all alerts that are having a certain label, for example, service X. That's pretty straightforward. Another more advanced feature is inhibition. It's actually pretty cool, even though rarely used, I guess, because it's not necessary that often. But it basically allows you to have certain alerts mute other alerts. So if you have sort of a higher priority alert, like your data center burning down, that's probably going to lead to all sorts of other things firing. But the person sort of on call for the service running in some rack in this data center probably won't really care or can't do anything about this incident. So there's no reason to sort of wake someone up if there's nothing to be done, no matter how critical it is. Coming back to anomaly detection. So of course everybody still wants it, and we have seen that Prometheus has apparently some statistical features like linear regression and everything. So maybe you can do something after all, just for fanciness. But just, first of all, this is just all bonus. These are things that might be nice and informative, but never make these things page you whatsoever, and don't ever rely on these catching critical conditions. That said, let's suppose we have a request rate for our service, which we sort of move into this new metric here called job request rate 5 minute. And we want to sort of get a smoothened view of this, right? Because it's sort of spiky, but we want to get the overall trend over the course of the day. And here we have hold winters functions in Prometheus, which allow you to add certain parameters, and what you get back essentially is this smooth red curve here, giving you a good representation of the overall behavior. Okay, so actually, if we have the smoothened view, we can actually build anomaly detection in a way. So let's say we want to sort of detect if the request rate right now is above or below a 20% sort of window around this smoothened view from 1 week ago. And that's exactly what we sort of reflect in this query here. So we take the current request rate, subtract the smoothened rate from 1 week ago, same day, same time, and check if it's out of the 20% window up or down. And then we can notify you in some hopefully non-invasive way about your traffic being abnormal. That's cool stuff to experiment with, but it will trigger on Christmas Eve, it will trigger on Super Bowl, all these times, right? Don't make these things page. Another example, and that's probably an example why it's really, really bad to do this stuff after all. So no need to understand this in detail. What we're trying to do here is we have the average latency over 5 minutes for a bunch of microservice instances. And we want to detect if one instance is out of the 2 times standard deviation of the average of all these instances. So one instance is being particularly slow. And 2 standard deviations is a pretty good measure, I guess. So that's exactly what we are sort of representing here. We take our current latency and check for every instance and check whether it's greater than the average of all latencies of all instances plus their 2 times standard deviation. And that's working fantastic until you realize that if all latencies are roughly the same, your standard deviation is going to be effectively 0, yeah. So now even the slightest sort of deviation will trigger this alert, pretty bad. So let's just change this condition with another condition. And we add a condition and tell it, okay, do all of this before, but only if we are in total 20% above the overall average. Cool. One sort of edge case elided, great. Until you realize that if you boot up an instance, it sort of has a cold cache and it's just being slow overall, but it doesn't matter because that's the warm-up period. But you will still get paged. So you have to sort of not consider any instance that has not received sufficient traffic so far. So we add another condition, all of the above, and you only fire off this thing if this instance has received more than 1 request per second. And here we have built a completely functioning edge case considering anomaly detection. And the point here is that we had a very well scoped problem. We knew what we wanted to solve. The data was very narrowed down from millions of series and billions of samples to just a few. And even then, with all our domain knowledge we have and knowing the cases we want to catch, it is really hard. And this is probably still not sufficient, right? So just rule of thumb, don't do this. Stick to symptom-based pages, stick to detecting violations of your SLA, and you are generally on the safe side. So summed up, symptom-based pages is what you want. You can add cause-based warnings. It's really helpful, right? If I see that my service is being slow and I can detect that it's because the database cannot be reached properly, that's great. But only page on symptoms. And design your alerts to be adaptive to change, right? Sort of be aware of dependencies between certain metrics like error rate and recurse rate. And preserve as many dimensions as you can, and explicitly remove dimensions that you are fault tolerant along to not page you if there's no actual problem happening. And for anything capacity planning related, linear prediction is probably what you want to do. Yeah, and you can do more stuff, but just stick with the basics. And the raw alerts we get from this whole thing, they are not really meant for human consumption, right? You need this alert management layer, which digests everything and gives you this nice, precise overview of what's happening, and gives you one page for one incident, and your incident is not measured by how many pages it triggered. And that's it. I think we have like 4 minutes. Any questions?
Yeah. Do you have any way of intelligent deduplication of alerts? So for instance, I have alerts generated out of an object. The cause might be the same, but there are too many similar instances where the constellation is going down.
So the question is if we have a way to intelligently deduplicate alerts. Okay. So the dumb way is if they have the same labels, they're exactly the same, right? We can deduplicate them, of course. If they're roughly the same, the point is if you have this grouping, they generally go into the same group. So in this case, we don't care about the individual alerts anyway. They would just go into the same group and be one notification anyway. So just based on this grouping behavior, it will probably not cause you to get paged twice or have any visible effect from these duplications, if they cannot be sort of deduplicated properly.
Do you have a set of alerts to monitor the infrastructure element like etcd?
Actually, yeah. etcd has in the GitHub repository for v2 and v3 set of alerts that are working.